Example problem. Oh, actually, it's 20.2. 20. Example problem 20.2 because that looks nothing like a 2. 20.2, force exerted on a violin G string, which is on page 743. Says this: a violin G string is 0.33 meters long and has a mass of 2.2 grams. Determine the force exerted on the ends of the string in order for a wave to travel at the speed of 128 meters per second. So some things we know. We know the length of the string, 0.33 meters. We know the mass of the string is 2.2 grams. We know our target velocity we would like to have is 128 meters per second, and we need to know at what force could we get that to happen. The equation or equations, they're both very related, that determine the speed of a wave on a string or some other medium. Velocity is going to be equal to the square root of the force of the medium on the medium, which sounds weird. The force of one part of the string pulling on another part of the string over this, I guess it would also be mu, the Greek letter mu. But in this case, mu is going to be representing something called linear density. Before we talked about mu as far as friction. Now it's linear density. What is mu equal to? It's equal to this, mass over length. So to me, this is the easier one to use. It's got everything we need. We got force, we got mass, we got length. It's going to be equal to velocity. One thing we need to change, units-wise, we always need to be in kilograms, meters, and seconds. This is in grams. So that would be 9 kilograms? Or am I off by one? 1, 2, 3. Yeah, or 2.29 times 10 to the negative third kilograms. Otherwise, it's pretty straightforward. So our velocity would be equal to square root of the force of the string on the string, which is sort of weird that we're talking about one part of the string pulling on the other part, over mass over length, or over mu. But I'll just stick with that. We're interested in finding force. Anytime that there is a square root that we want to get rid of, we have to square both sides. So by squaring this and by squaring that, we now get rid of this square root. And we are left with velocity equals force of the string on the string, or the force on the medium, times m over L. Well, if we think about what m over L would be equivalent to, divided by, this actually should be velocity squared. Oopsie. So this thing, force divided by meters divided by length, would be the same as if length was on the top. And it, to me, is easier to think about that way. Force of the string on the string times length over mass. But of course, we're trying to find force, so we want to get force by itself. We're going to have to multiply each side by the reciprocal. That would cancel these. We'd be left with force alone. So mass times velocity squared over the length is going to tell us the force that we're going to need to apply on the string to get it to vibrate with a speed of, I think it was 128 meters squared, or meters per second. So our mass was 2.2 times 10 to the third, negative third kilograms. our length of string, 0.33 meters. If that was centimeters, remember that you would have to make sure to change that to meters. Times our velocity squared, 128 meters per second. That whole thing squared. It's going to give us our force. What you end up with by the time you cancel everything is 110 kilograms times meters per second squared, because the meters are going to cancel. Well, kilogram times meter per second squared is equivalent to the Newton. So 110 newtons would be the amount of force that you would need to apply to make it move that fast. If you cranked it down, applied more force, it's going to go faster. If you loosen it up, apply less force, it's going to go slower.